All right, so 4.4 is called integration by U substitution, also pattern recognition. We talked about U substitution a little bit in a couple sections ago, and you would have been like, wow, that looks like magic. How does that work? We'll show you again in this section. But a lot of the times when you can do the process called U sub, pattern recognition works equally as well without doing the formal U sub process. But of course, in order to recognize patterns, what has to happen? You have to learn what the patterns are, right? And then in order to recognize them in the future, you have to kind of work with them quite a bit, which means you have to PPP, which means do the worksheet, essentially. Practice, practice, practice. Yeah, that's how you become good at this. That's how you recognize patterns, by working a lot of problems and getting good with recognizing the pattern. So let's start off with example 1. Because U substitution and pattern recognition are going to be viable integration methods when you have composite functions. And what is a composite function? Function inside of a function, right. So example 1, we're taking the derivative of a composite function, right? And for that, we have what rule? How do we take the derivative of composite functions? What rule? Chain rule. Good, chain rule. So we count the number of layers. We have tangent on the outside. You go on one layer and you see e to the blob. That's the second layer. And finally, the exponent is the innermost blob, 4x squared. So with 3 embedded functions, 3 layers, how many factors will we have in our derivative? 3 layers means 3 factors. So it's a good way to take account of what's happening. All right, so without me telling you how to do it, because you know how to do this, you take the derivative, I'll take the derivative, and see if we get the same answer. Okay? This for background music would be good. I use different flavors just because it helps me. You don't have to do that. On the AP exam, you'll probably just have one flavor, lead. Don't taste lead. It's poisonous. It's not really a flavor. Nowadays, pencils are graphite anyway, right? Go ahead and taste the graphite. It's good for you. Ooh, I like that. Yeah, the relief. Okay, did I get it right? Will said yes. Thank you, Will. Let's see. We work from the outside in. The derivative tangent of blob is secant squared of the blob. That's the red version. You go on one layer and you get e to the blob. Its derivative is e to the blob. That's the purple nurple layer. And then the root of 4x squared is 8x. Good. So we have 3 factors. Now, if you notice, when we do the chain rule, it's kind of like we're unpacking boxes. And I think they used that analogy back in the day. So we have this one big box, and inside of it we have another box, and inside that box we have another box. So as we unpack boxes, the contents get smaller and smaller. You see that? So the first factor is the bulkiest, right? It has more information. The next factor is a little bit smaller with information, right? We have one less function. And then the final layer is the smallest factor. It has less information, right? So when we turn it around and write it kind of in a nicer format, now we have them in increasing order of size. We have the factor 8x, which is the smallest, e to the 4x squared, which is the next largest factor in terms of information, in terms of inside functions themselves. And then the last factor is the biggest, bulkiest factor of all, right? Secant squared of blob to the blob, okay? So what we are going to be doing in this section is finding antiderivatives again, indefinite integration. And remember, that process is really the idea of finding a function whose derivative is the integrand that we're starting with. So we're having to guess functions whose derivatives give us the function we're staring at. Okay, let's mosey on down to example 2. In this question, it's asking us to evaluate back to the indefinite integral. How do we know it's indefinite? Yeah, there's no numbers there. There's no intervals of integration, as we call them. And so our answer is going to be an indefinite answer with the plus c. So we're trying to guess now the function whose derivative is that giant integrand. Goodness gracious. We have a product of 3 factors, 8x, e to the 4x squared, and secant squared of e to the 4x squared. And there is no product rule for integration, and there is no quotient rule for integration. So we're stuck just trying to guess, I guess, at the very least, what the function might be whose derivative is that. Any ideas? Gosh, where to start? Look at example 1. Anyone?
Tangent of e to the 4x squared.
Plus what?
Plus c.
C! How did you know that?
Because we just did it.
We just did it. Good. So, really, this whole section is about me asking you to find antiderivatives of integrands that have multiple factors right after I ask you in the previous question to take the derivative of something that gives you that, right? That's all the pattern that you have to recognize, right? Is that how it's going to work? No, hopefully no. No, because that's too easy. No, hopefully not. That would be boring. That would be very boring. You would want to get out of bed in the morning and come to class. So that was the right answer. Good job. But how do we arrive at that if we didn't do that up here previously? How do we arrive at that on our own? That's what you're going to learn, okay? So because there is no product rule or quotient rule for integration, when you walk up to the problem, you're like, what's up, problem? You identify, first of all, how many variable factors you have. In this case, we have 3. Every factor but one then has to come from the third factor in this case, inside function, all right? So which of these 3 factors is the biggest, baddest, bulkiest factor of the 3? Secant squared. So that's your first thing. When you notice you have multiple factors, whether they're multiplied or divided, and you have composite functions, identify the factor that has the most information in it. It's that one. Okay? And the next step then is to identify the inside function for that factor. You want to identify the inside function. So what does that mean? Well, we're talking about composite functions. You might be better off identifying the outside function first, because you work your way from the outside in, right? So if you do that, when you walk up to the problem, you might spy a secant squared of blob. So secant squared could be the outside function. So if that's the outside function, what's the inside function? Well, what's inside of it? E to the 4x squared. So that could be your inside function. Now, remembering that this came from the chain rule, the other 2 factors then in this case, if it works, have to come from the derivative of this inside function. Okay? So we're going to check. Could it be that the 8x and the e to the 4x squared then came from the derivative of this function? Let's quickly check. What is the derivative of e to the 4x squared? E to the 4x squared. So that's where that factor could have possibly come from. And then because it has its own inside function, times the derivative of e to the 4x squared is 8x. So indeed, boom, that's where the other 2 factors came from. So if the derivative is unpacking the boxes, anti-differentiation is what? Packing them back up. So what we're going to do now that we've correctly identified the inside function that generated the other factors, we're going to pack the 8x back up into the 4x squared, and now it's gone because it's in this box. And then we're going to take the e to the 4x squared, and we're going to package it back up inside there, and now it's gone back inside its box. And what we're left at, looking at then, is just a single factor. And now, once we do that, it's time for the actual integration process. What is the outside function containing the inside function? Secant squared of blob. There can only be one rule of integration, and it's always going to be the rule for the outside function. So now the question is, what is the antiderivative of secant squared of blob? Tangent, right? Tangent of the same blob. And then, of course, we put plus c. And that's basically how you go about analyzing each and every one of these. But the good news is, if you're not sure if that's correct, what could you do? Take its derivative. And I would strongly encourage you, especially in the beginning, to check your answers because it reinforces the process. Because what most people have a hard time with when we're going backwards is they're like, where did the 8x and the e to the 4x squared go? How come they're not in here? Like, they are. They're just packaged back up inside the box. You can't see them because you're staring at the outside box. Okay, but if you open the lid and go take a look, you'll see them. Well, let's take the derivative. When we take the derivative again, which I think we just did, well, let's do it again. Tangent of blob is secant squared of the blob. Okay, good, got it. Times the derivative of the next layer is e to the 4x squared, times the derivative of 4x squared is 8x, and of course c goes to 0. And that is, in fact, what we started with. All right, so we can check. All right, ready to try another one without doing the derivative first? Speaking of derivative first, notice that the actual first step in this process was looking at the derivative of the inside function. So the first step of integration is really checking a derivative. All right, so let's jump down here, skip all that, example 3. It says to evaluate using U substitution or pattern recognition. I'm going to do pattern recognition first. So you walk up to the problem and you spy two variable factors, right? X squared plus 1 to the 12th and 2 times x. Now, without any advanced techniques like we're learning today, there is a way to do this one. All we have to do is what? Simply expand out x squared plus 1 to the 12th power. How fun is that going to be? Not fun at all. And then when we finish that, we can distribute the 2x all the way through to each term, and then just do the power rule all the way down the line. No, thank you. No, thank you. But if that were just x squared plus 1 squared, then that would be probably an option, right? So there has to be a better way, and I hope there is. So, again, we have a product of two variables, functions. Which factor is bigger, badder, bulkier? The 2x or the x squared plus 1 to the 12th power? Yeah, I think that's pretty obvious, right? And so the outer function would be blob to the 12th. That's your outside function. And your inside function could be x squared plus 1. So could it be then that the other factor of 2 times x came from the chain rule when we took the derivative of that inside function? Well, let's see. What is the derivative of x squared plus 1? 2x. Haha, it is, in fact, where the 2x came from. I don't know who took the derivative, but somebody did. And when they did, the 2x came from the chain rule. Well, our job is to package it back up. So the 2x now, we're going to package it back up. So this arrow now goes really the other way. 2x, you go back inside that box, and it's gone. And since there was only one other factor, we only had to package up one thing. So now you're already at step 2. Once you reconcile that, you're on to step 2, which is the rule of integration. What would be the integral of x to the 12th? How would you do it if it were just plain old x to the 12th? The antiderivative would be x to the 13th divided by 13, or times 1/13. Same thing here. We're just going to call it blob. So blob to the 12th becomes blob to the 13th. And then we'll put the reciprocal of that in front, plus c, and the blob just goes right there. And I claim that that's the antiderivative of what we started with. Let's check it. Get rid of all that and let's check it. Check. All right, so if we're taking the derivative now, it's the chain rule. You walk up to the problem, you see 1/13 blob to the 13th. So multiply and you get 1 times x squared plus 1 to the 13 minus 1 is 12th power, times the chain rule, the derivative of x squared plus 1, which is 2x, and the derivative of c is 0. Is that the original integrand? It is. Okay? So that other factor is going to go away because you're packaging it back up into that inside function. It doesn't matter how many factors you have. You can have 5 factors. 4 of them then come from the chain rule, and they all get packaged back up sequentially, one inside the other. All right, so let me show you the process of U substitution. It accomplishes the exact same thing, but it's a few more steps. And there is merit to it, as you'll see later in the section. Sometimes it's actually required. It still involves identifying the inside function. So we're going to say let U equal x squared plus 1. And U is just an arbitrary variable, and it's going to become a placeholder for that inside function. Because what makes this thing problematic to begin with is because it is a composite function. So by replacing the inside function with a single letter, it makes it a lot easier to do. So our goal then is to rewrite this entire integral, which is a function of x and dx. We want to write it now equivalently in terms of this other variable called u and du. So I'm going to go ahead and start replacing as I find things. So the first thing I'm going to replace is instead of x squared plus 1 to the 12th, I'm going to call it u to the 12th. That already looks better. But notice I still have to replace the 2x, and I still have to replace the dx. So because you're always going to need dx, you're going to always then take the derivative of what you're calling u. So we'll take the derivative with respect to x of both sides. So du dx is the derivative of the left, and what's the derivative of the right with respect to x? 2x. All right, so let's go ahead and solve that for du. If I multiply both sides by du, I get 2x times dx. You could treat those as individual quantities. Now, looky there. It's my lucky day. I wanted to replace 2x and dx, and I thought I might have to do it with two separate substitutions. Well, look how fortunate I am. I can replace the 2x and the dx with a what? With a du. Boy, that's nice. And so that right there becomes the equivalent integral in terms of a different variable. Now, what makes this one nicer? This is no longer a product of two functions, is it? It's just a single variable raised to a power with respect to that variable. So at this point, this could be the integral of x to the 12th dx, p to the 12th dp. It doesn't matter. It's simple. It's just a little power rule, isn't it? It becomes u to the 13th divided by 13, or times 1/13 plus c. Now, the last thing we have to do, since the function started off as x, and u was just a temporary placeholder for that quantity, we now have to substitute back in what u actually is. So, one of my favorite things to say in here, one of my favorite questions is, what is u? X squared plus 1. Yeah, it's one of those times where that sounds horribly incorrect to say it like that, but it's a legitimate question. It's x squared plus 1. And if you compare that with what we got over here, we get the same thing. One method requires one line. The other method requires lots of lines, more than one. Okay? So when we do the pattern recognition in our head, what we're really doing is use substitution in our head. And this is the magical step right here, replacing the 2x dx with the du. We do that when we mentally check the derivative of the inside function to see if we get the other piece right there. And then when we package it back up, it's the same thing that happens over here when we replace it with a single du. It's kind of the same idea. And then, of course, instead of calling it u, we call it blob. And we just say blob to the 13th times 1/13th. And we go ahead and write the blob in there, and it saves an extra line of writing. So it's really the same idea, but you're just doing it in your head. Okay? So the previous two problems have worked out beautifully because the derivative of the inside function was exactly the other factor, in this case 2x, and of course up here we had the 8x and the other piece. It's not always going to be like that, but it's nice to start that way. So let's take a look at example 4. You walk up to the problem and you spy one variable factor and another variable factor. Two variable factors. Can we just use the product rule for integration? No, it doesn't exist yet. Maybe you'll find it someday. Win a math prize or something, or a ribbon. But until that day, we have to do it a different way. So there is no product rule. We have to identify the pattern or use u substitution. So again, the mental flow chart's the same. Of those two factors, which one looks more complicated, has more information? The sign of the blob, yeah. So it's going to contain both the outside function, which becomes ultimately the rule of integration, and it contains the inside function, whose derivative hopefully is the other factor. Well, let's see. The outside function, I guess, could be sine, right? That's your outside function. I mean, you walk up to the problem, it's like, hello, sine. So that's your outside. You don't even have to label them. So I will for now. And so what's inside the sine function? 2x to the fourth plus 1. So that's what we would call the inside function. And here's what we do. We check. We check. Could it be that 3x cubed then came from the derivative of 2x to the fourth plus 1 when someone, not us, took the derivative to get that? Well, let's see. The derivative of 2x to the fourth plus 1 is 8x cubed. Crap! It doesn't work. Lay bummer. French for the bummer. You know what? I think it still might work. Here's why. I get the x cubed part, which is the variable part. And that's actually the only part we need. Okay, let me write over here. You can be off. You can be off by a constant multiple. No problem. What you can't be off by is a variable. So as long as you generate the critical x cubed part, you've got it made. It's going to work. And let me show you then how you would handle that. Backing it up then a little bit, we're going to have kind of a new first step. The 3 was no help. I wanted it to be an 8. So in general, like we did previously, if you have a constant multiple that's already in the problem, whether it's an 8 from the first problem or a 2 in the second problem or a 3 now, regardless of what it is, pull it out front. Don't let him influence any decisions that you're going to make. This is a systematic approach to this process. In fact, 3 is already in my final answer. See him down there waving? Hey, I'm down here, guys, waiting for you. If he's in the beginning problem, he's going to be in the end answer. He's a rider. I call him a rider. He just goes along for the ride all the way through. He's in the back of the truck. You don't even know where you picked him up. You just looked back there and he was there one time. And you let him stay. He's the rider. Now we could do this. Now we'll do our analysis. The derivative of 2x to the fourth plus 1 is 8x cubed. And you could say, dang it, I'm off by an 8, by a factor of 8. Dang it, if only I could put something then in my final answer here to neutralize that unwanted factor of 8. Just like when I know I'm going to go eat a big old steaming plate of enchiladas, I take some Tums beforehand to neutralize the unwanted acid that I'm going to get. What could I have in front of my answer there to get rid of the unwanted factor of 8? What constant? A 1/8. Why a 1/8? Because what's any number times its reciprocal? 1. 1. So the 1/8 is the Tums to the unwanted 8, which is the enchiladas. Now I'm hungry. I call this a correction. You can have a correction by putting the reciprocal of your unwanted constant multiple in front. And that's not a problem at all. Okay, so now that we have a correction there to correct the unwanted 8, guess what happens with the x cubed? Now the x cubed gets packaged back up and it's essentially gone. And you move on to the all-important step, which is the integration. What is your inside function 2x to the fourth inside of? It's inside of the sine function. And what's the antiderivative of sine? Negative cosine of the blob. And you are done. Okay? This negative here is your rule constant. And that's the most you'll ever have. A correction, a rider, and a rule. Have a great weekend.